Reference angles. Find two angles between 0 degrees and 360 degrees whose sine is the same. What does it mean to have the sine be the same? Well, recall from our previous videos how sine can be thought of as the y value. So what we're looking for is to have the same y value. So if we think about how in quadrant 1 is probably going to be the easiest thing to understand here, if you're thinking about some point along quadrant 1, let's call it x comma y, what we want is to have the same y value. And if we need the same y value, then that must mean that we want to be somewhere along the unit circle that gives us something along this line here. Well, we see that occurs right here. Okay, so let's say, for instance, that I know it's not going to be drawn to scale here, but let's say that this point gives us an angle of let's say 45 degrees. That looks like about 45 degrees there. Okay, so if we find that 45 degrees is there, what we want to find is sine of 45 degrees is equal to what other sine that gives us the same y value. So if we take a look at the diagram here, you'll see that 45 degrees brings us to this y value here. But if we keep going all the way around, we'll see that we get the same y value when you come to this point right there. That's where they're going to have the same y value. And so the idea here is, well, what exactly is this angle measure, right? Well, if you notice, our triangles actually look kind of symmetric. If we develop triangles here, right, here's a right triangle, you can develop another right triangle here, which means that in this triangle, this must also be a 45-degree angle. That's why they would have the same y value, right? They would have the same y value. They both go up the same amount. So if this angle is 45, then what we want is actually to find this angle, because remember, we always measure angles from the 0-degree mark and work your way counterclockwise. So what is that? I think that's going to be 180, which is a half circle, and take away the 45 degrees. That's going to give a measure of 135 degrees. So sine 45 degrees is equal to sine 135 degrees. Let's do another example. Let's say we establish sine of 30 degrees. We want to find another angle that gives us the same sine. So sine of 30 degrees means we're going to go 30 degrees up. It needs to have the same y value. Where will that be? We need to have another 30-degree triangle in quadrant 2, right? Well, if we go with a full semicircle again being 180 degrees, hopefully what you see is that the rest of that angle, sine of 30, is the same as sine of 150 degrees. Okay, one more. Let's just do one more for good measure. Let's say we have sine of 60 degrees. Sine of 60 degrees is the same as sine of, I'll give you some time to think about that. And hopefully what you're thinking here is sine of 60 degrees is equal to sine of 120 degrees. What's the pattern here? Sine of any given angle measure, sine of theta degrees, is equal to sine of, how are we getting those other numbers? Hopefully what you see in the pattern is you're doing 180 degrees minus theta degrees. So this is a property that you can establish in order to get the same sine measure. I'll let you do the same thing for cosine. And then that's going to bring us now to something called a reference angle. A reference angle is a positive, acute angle formed by the terminal ray of angle theta and the x-axis. Okay. So as we had seen up above, what we're going to do is develop an angle that is acute, meaning keep in mind that acute means that it's an angle that is less than 90 degrees. And it also has to be positive, so keep that in mind, that a reference angle always has to be positive. So I'm going to give you, let's do 3 examples here and examine what exactly a reference angle is trying to tell us. So I'm going to go ahead and draw some coordinate planes here. Just some arbitrary coordinate planes. Let's just do 3 of them, just to see what's going on here. Okay. So for our first example, if I develop an angle measure that is, actually let me do this over here, like this. Okay, and we're going to go from degrees to radians. Okay, so what we're going to do is we're going to establish that this particular angle measure is an angle of 5 pi over 6 radians. One thing that we have seen before is that in transitioning degrees to radians, we know that pi radians is the same as a semicircle, a half a circle, 180 degrees. So this is going to be 5 pi over 6. It's quite close to pi, but not quite there. Now, if we want to find its reference angle, keep in mind our definition is we're finding a positive acute angle formed by the terminal ray of angle theta and the x-axis. The terminal ray meaning the red line that we've already drawn here, and the x-axis. So if our x-axis is right here, then the reference angle has to be an acute angle. You have three choices here. Is it angle 1? Is it angle 2? Or is it angle 3? Think about which of these angles, 1, 2, or 3, satisfies the definition of reference angle in terms of what is positive, acute, and with the x-axis. Keep in mind this important part too, with the x-axis. Okay? Because it's with the x-axis, we actually can rule out example number 2. It has to be acute. Well, that's not what 5 pi over 6 is. That's not acute. That's not less than 90 degrees. So that's not angle 1 either. Angle 3 would be our reference angle. And how do we call this reference angle? Angle 3 is, what you'll notice is you're going up in this direction with the x-axis. You're going up. Instead of going counterclockwise, you're actually going clockwise. And this angle here, if we figure out just a little bit of arithmetic here, we know that an entire semicircle is a value of pi. And what we're doing is taking away the 5 pi over 6. And in doing so, we end up getting the rest of that, this reference angle here, of pi over 6. So our reference angle is pi over 6. Okay. Let's take a look at example 2. If I now draw an angle right here in quadrant 3, and this time we're going to establish that this angle measure, let's call this an angle measure of 7 pi over 6. Okay. Remember our definition of a reference angle. It needs to be acute. It needs to be with the x-axis. It needs to be positive. So think about it like this. I'm going to give you three choices again. Is it angle 1? Is it angle 2? Or is it angle 3? Or is it even angle 4? Okay. Let's backtrack. Angle 4? Is that an acute angle? No, that's obtuse. So it's not angle 4. Angle 3? Is it that one? No, it's not with the x-axis. It's with the y-axis. So we don't want that angle either. Is it angle 1? No, that's obtuse. We don't want that. Ah, must be angle 2 then. Angle 2 is our reference angle. So how do we find that? Well, in this case, what we see is that the total angle measure that we definitely know is 7 pi over 6. And you'll see that you just want this angle measure here, and you don't want all of this. How much is all that? That's a half a circle, a semicircle. So you want to subtract the value of pi. That's a semicircle. So 7 pi over 6 minus pi, if you just kind of do common denominators, then that's going to give us a reference angle of pi over 6. Again, this has the same reference angle of pi over 6. Okay. Example 3. I'm now going to draw an angle in quadrant 4. Let's go here. Okay, and we're going to say that this whole angle, remember starting from the initial ray, is going to go all the way around like this, and this is going to be an angle measure of, let's say, 11 pi over 6. If that's 11 pi over 6, we want to find its reference angle. Let's think about this. Is it angle 1? Is it angle 2? Is it angle 3? Or is it angle 4? 1 is definitely way too large. That is not an acute angle. That's not it. Is it 2? It's with the x-axis. Oh, but it's not acute. Right? This is a bigger angle than 90 degrees. So that's not it either. Is it angle 3? That's acute. Oh, but it's not with the x-axis. This is with the y-axis. So it's not angle 3. So our reference angle is actually angle 4. And how do we find that? Well, we know that a full circle going all the way around is a value of 2 pi. That's 360 degrees. And we know that what we have here, this angle measure, is 11 pi over 6. So we take away the 11 pi over 6, and what you're left with is the rest of that angle 4 right here. Okay, so in doing that, you can go ahead and get common denominators. 2 pi, that is the equivalent to 12 pi over 6. Look at that fancy work there, huh? 12 pi over 6 minus 11 pi over 6 gives us a reference angle of pi over 6. Again, we have a reference angle of pi over 6. And that's our angle 4 that we see there. So that's reference angles. Let's take a look at an example of applying the reference angles to doing a problem. For each of the following, so what you're going to do is when you come to class, you're going to be working on these problems here, but we'll just do the first one together. This will be number 3, A and B. And then in class you'll do 4A and B, 5A and B, and so on. Okay, but what we're going to focus on here is x equals 130 degrees. I'm going to go ahead and establish a drawing again, show your work. And so if we have 130 degrees, where does that place us? 130 degrees will place us somewhere here. This will be 130 degrees. Okay. All right, so where's this reference angle? Is it here? Is it here? Is it angle 1 or is it angle 2? Hopefully what you're seeing is that with the x-axis and it being acute, it must be angle 2. So we don't want this angle here. So how do we find that? The reference angle is going to be a total of a semicircle, 180 degrees minus 130 degrees. And so we see that the reference angle is going to be 50 degrees. Okay, so I'm going to go ahead and call my reference angle 50 degrees here. And I'll classify my reference angle as this letter alpha here. Alpha is the reference angle. Just using more Greek letters. And then for B, write the given trig function in terms of the reference angle. So we're still using the 130 degrees, but now we're trying to find cosine of 130 degrees. Now this is actually something we have to apply to what we have learned in a previous video. Recall in a previous video, depending on which quadrant you're in, using ASTC, it helps you identify what trig ratios are positive. Because 130 degrees places us in quadrant 2, we know that all the sine trig ratios are positive, but every other trig ratio is negative. Now, because we have cosine, that's telling us that we actually should have a negative value. Now, in terms of its reference angle, remember 130 degrees has the same reference angle of 50 degrees. So this is really the same as saying cosine of 50 degrees. However, because cosine in quadrant 2 gives us a negative value, you actually have the negative value of cosine of 50 degrees. And so cosine of 130 degrees is equivalent to negative cosine of 50 degrees. And here I just wanted to show you on the graph, on the calculator, how this holds true. Okay, so I'm going to go ahead and open up my calculator. Okay, and put these side by side. Okay, so what I want to show you is that if we establish that we have cosine of 130 degrees, I'm going to go ahead and type that in, cosine of 130 degrees. Notice how we get a value of negative 0.6427, blah, 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 right? Now, if we do cosine of 50 degrees, its reference angle, notice you get a value of 0.647. So that's why it's important. You have to use your understanding of ASTC, of which quadrant you're in, to make sure you put in the negative sign. It's not enough just to say cosine of 50 degrees. You need the right signage as well. Okay, so here you'll see that cosine of 50, this part gives you the 0.6427, but then you have to add on the negative yourself. So we get the same value, negative 0.6427. Okay, so I'm just showing you there how ASTC is very, very important. It's crucial in making sure you get the right value here. Okay, so you'll do the rest of this in class, and again, you need to think about what ASTC means.